Go ahead and start the morning session. So our first speaker is Paul Fendley, and he's going to talk about lattice topological defects.
All right, thank you, and thanks to Eric and all the organizers for having me here for a while. It's been fun already, continues to be fun. So I'm going to give a talk this morning that a priori doesn't seem to have a whole lot to do with entanglement. However, I hope I'll show that it's not completely orthogonal either. In fact, I think basically everything I say can be phrased in the language of tensor networks, and I'll indicate how that goes. But one of the morals of this talk is there's an old story that really isn't very different from the new story. Anyway, so let me tell you about some old stuff. Most of the stuff on this slide happened in the 80s. One of the most, I think, deepest results in mathematical physics was Jones' discovery of knot-invariance, the Jones polynomial of knot-invariance. And that doesn't sound like physics unless you think tying knots is physics. But what happened almost instantly after his work, and in fact, I'll explain a second before his work, is that this led to a huge amount of progress in seemingly very different areas of physics. So Witten, for example, not long after, showed how you could set the Jones polynomial inside Chern-Simons theory and the computations reduced there. And then this exploded into a whole field that many mathematicians still spend their entire lives studying in the name of topological quantum field theory. Right at the same time as Witten's work, there was beautiful work by Moore and Seiberg on rational conformal field theory. So in the late 80s, when I was a grad student, conformal field theory was the fad in string theory. The two fields were isomorphic. Joel Polchinski wrote his book in the conformal field theory version and then rewrote it and stuck those chapters at the end. That's, I don't know if you know, that's why those chapters are at the end of his book. But everyone then thought that that was the problem in conformal field theory. That's mostly been forgotten with D-branes, et cetera. But in those days, so what Moore and Seiberg did is they showed if you wanted to understand what sort of the superstructure, or more, I should say, or maybe a more abstract structure underlying conformal field theories, it was the same mathematical structure that Jones found and that Witten studied as well. And another one that's come up, and the reason this work has come back into physics, I think sociologically, is theories of anyons. And so, I don't know, have we had any topological quantum computation talks? I guess we haven't, but there are many talks on that. Microsoft is spending $1 billion or something like that to try and detect and manipulate these things. But the story I'm going to tell you about, while mathematically identical to the mathematical structure I'm mentioning in all these stories, is in fact the original one. In fact, it predates Jones' work. And this is lattice models of statistical mechanics. So Jones essentially independently rediscovered a lot of this, but it was known, some of it more than a decade before him, that the algebraic structure underlying the Jones polynomial came up in a lattice model. So I'll give more details on what that is. And so the structure is called a tensor category, and that sounds scary. I remember years of my friends at Station Q using the word category and my being frightened. It's really not that frightening. In fact, it's suitably abstract that it's, I think, simpler. You don't have to keep track of much of anything, and I'll tell you what you do need to keep track of. But the key thing is, in all of those theories I listed on the previous slide, the key structures are, in all those things I did in the previous, these theories I listed in the previous slide, all they have something to do with braiding and fusing. So in the conformal field theory, you can talk about operators, or actually they're chiral parts. And you can ask, well, what happens to the chiral parts of the correlation functions, what are called conformal blocks, as you take one operator around each other. And you can think of that as sort of a braiding process if you think of some fake time dimension. In an anyon theory, again, you think now it's actual time as you take a particle around each other and ask what its statistics are. And so these are braiding processes, fusing processes. You ask, well, you take two anyons and you glue them together and treat them as a composite particle. Well, then what are its properties? And when these things are not abelian, as they are in most all examples of that, all difficult, well, I shouldn't say all difficult. Many examples that people study, well, it's a whole long story, and you need a mathematical structure to see that that's all consistent. And this is called the tensor category. And again, I'm not going to give you many details. I'll tell you what I need from them in a second. But the thing to emphasize, so mathematicians have studied that there's all sorts of different types of categories, which can be very frightening. I'll make all these assumptions I'm not even going to tell you about to mean I don't have to put arrows on my diagrams, and lots of things are simple. But anyway, they've classified these sets of rules, but I'm a physicist still, and so what I want to do is use these rules. And what I'm going to use these rules for is I'm going to take my lattice models in statistical mechanics, I'm going to rewrite them in a way that I can exploit these rules. And then it's incredibly powerful because what it lets me do is do calculations by drawing pictures. So by the end of the talk, I'll explain what that diagram is good for, but what all you need to know now is this is some diagram. And so you draw links, you label them, they may go over, so this is just some 3D thing that I've projected down into the plane. I have all these things, I have branching where these three come together, and so forth. But the point is these rules tell you how to turn this thing into a number that will basically only depend on the topology of this picture. So it's a topological invariant. Obviously, it will depend on all these labels, A, B, C, and if you're doing an anyon theory or that would label what type of anyon in a conformal field theory, would label what operator you're there. We'll see what they correspond to in the stat mech models in a bit. These are just numbers there, and this will be some matrix element that at the end I'll write what it is. But the point is, I can use these rules to compute that number, and I'll tell you a little bit more about how it goes. So I guess actually what I say. So in particular, the rules allow you to take some diagram and manipulate it, make it simpler and simpler to the point where you can write down the number. And that's how the Jones polynomial works. It's kind of, you write down your knot, you project down a plane, you do a bunch of rules, and out spits a number, or polynomial. But it's the rules that we're going to use, and because they're the same rules in all these cases. In Chern-Simons, it would be computing expectation values of Wilson loops. All right, so let me tell you just a few of the rules. And in fact, this slide, the next couple slides, will pretty much get most of the rules, lots of details skip. But the key object that I'm going to use is, if you wish, fusion. So you have, again, so these lines we draw, if you want to think of anyons, think of these as anyonic particles or operators in a conformal field theory. And we just label them by A, B, and C. So one of the things, we'll assume that these labels take values in a finite set. And if you've heard of what a rational conformal field theory is, the rationality is what means those labels, there's a finite number. If you're doing higher dimension conformal field theory, that's not true anymore. So we're not going to do higher dimensional conformal field theory. And so then you can think of this as a diagram to somehow represent particle A, particle B fuses to particle B if you want. More formally, it's a fusion algebra, so A tensor B, it gives you C, and these NABCs are just numbers, in fact, integers, non-negative integers. And if this non-negative integer is greater than 0, this vertex, we can draw pictures. If it were equal to 0, you can't draw pictures with that int, or those pictures are just 0. Everything we do will always look at the case where NABC is 1, but it all works in general. So again, if you like conformal field theory, you like anyons, you like Wilson loops, you like whatever, you can think whatever your favorite thing is, and you can fuse two things together, and you get something else. And again, since most people here have come up with the Ising model in one context or another, the famous fusion rule there is we have the sigma, which is the chiral part of the spin field if we're doing CFT, fuses together, and it can give you either the identity or it can give you something new. And so then we would write down that vertex there. And Yeah, so that's the, and it says topological, so I can rotate this diagram, everything's all the same. So that's the basic building block. And on this slide, I'll give you most of the important rules. So I'm going to write down diagrams, and then I turn them into numbers by using these rules. So here's kind of the most important one. If I have just a loop not connected to anything else, well, to evaluate this diagram, to turn it into a number, it just gives me this number d sub a. And Hubert yesterday mentioned n in StatMech. This is usually called n, but we call it d, so it goes. And it's called the quantum dimension, and it's actually kind of a good name because if you think of these as particles, d sub a tells you kind of the number of particles that are running around that loop, if you want to think it that way. It doesn't have to be an integer, hence the quantum bit, but anyway, so I think that's slightly useful. For icing, the quantum dimension of the identity, so d sub 1 is 1. This psi, the fermion field, is 1, but then this spin bit is square root of 2. So this one, I actually don't need braiding for much of what I do, but since it's so intuitive, and this is how the Jones polynomial works. So it says, again, you have these 3 lines, and then with each category, you associate the number d sub a with each type of particle, or in the category language, object. And here there's another number, which in the conformal language or anion language is the spin. And it says is if I, what happened to this? Sorry, this is what happens. I lost a picture. That's supposed to be, this thing gets turned into that thing, well, rotated by 180 degrees. That's embarrassing. So it's not, this doesn't turn into a number as the picture would indicate. What happens is, it's easier to just say, I untwist that. Sorry, major typo there. So you just untwist that, and then you get this phase. And that has to do with the braid. But anyway, this is the more important one for what I'm doing. So this is called an F move, which is a pretty bad name. The F is for fusion. But if you just think now angular momentum, so if you think A prime, B prime, A and B are 4 spin-and-a-half particles, and you say, let's make a spin singlet out of them. Well, I can do that in different ways. I can take these 2 spin-and-a-halves, and I can make this, say, a spin 0. And so then C would be 0, or I can make it spin 1, and then C would be 1. And both of those will give overall spin singlets, because I can take 1 with 1 and get a spin singlet back again. Or I could have done it with these particles. And that's just a basic, this matrix does that. And if that last 30 seconds didn't make any sense to you, just think of it as a rule again. I get a picture, and I can replace it now not with one picture, but with a sum over pictures. And again, that's not supposed to be a C there, I'm sorry. Too late last night. There's no C there. Anyway, sum over these pictures to get that. And F, you can think of this as a matrix, and for icing, that's the matrix. And the key thing is about, so when you have these rules, you can just go to a list, you can go to a mathematician, and they tell you what these numbers are. At minimum, they tell you they exist, and you can work them out. But in many cases, you can go look up in some appendix of a Reshetikin paper or something, and these numbers are there. So we're exploiting this structure. So that's enough about the math. So, yeah. Yeah. Yeah, so it's square root of 2 times square root of 2 equals 1 plus 1. Yeah, it's consistent with the fusion rules. Yeah, that's fair. Okay, so anyway, so let me summarize what I've said. Now I'm going to get to physics in a second, but let me summarize rules. So what the rules buy us is now in these lattice models, we find topological defects. And I'm going to use this. So the strategy, I set up the lattice models in a certain language using these pictures. And then once I do that, it's really easy to find topological defects. And if you don't know what a topological defect is, I will tell you. And this is all on the lattice. And so we can find them in lots of models, greatly generalizing what anybody did before everybody was... people have done work on this, of course, but either in CFT or on the lattice, it was sort of ad hoc. We can make junctions of them, and one of the consequences that I'll explain is that you can greatly generalize what's called Kramers-Wanier duality, the duality of the Ising model or the Potts models. So those are lattice things. But then what we can do is we can do lattice calculations to get things. Famous old result of Ian and Andreas Ludwig's is the G factors. Again, if you don't know what it is, I'll tell you. And we can compute them exactly on the lattice. But of course, this is an exact number. And if you take the continuum limit, well, it's the same number. Assuming the limit exists, it's the same number. So it's an exact lattice calculation out of a continuum quantity. And as I'll show you, it's pretty easy. And in fact, we can even push it further. We can do modular transformations. And then there's a trick, again, that lets you get exact dimensions of operators. So I think it's really remarkable. These are purely lattice calculations. They're exact, they're rigorous, but they yield numbers that, if you believe the continuum limit exists, then must give the correct numbers for the corresponding field theory. And it doesn't have to be critical, by the way. Most of the examples I'll use are critical, but these topological defects exist in many theories, and most are not critical. All right, so let me explain now, try and give you a picture of how the setup is. So what I'm explaining now is the setup of how we turn a lattice model into these pictures. So I'm not going to do this in all detail, but on the other hand, hopefully give you enough of an idea so that you believe me. All right, so this is we've got some lattice model living on the square lattice, and on every site in this picture, on the site of the square lattice, we give it in some integer value, to make it easy, integer value degree of freedom that people typically call heights. And so I just labeled some of the sites there. Now the partition function, like all partition functions, we could write this as e to the minus beta e in the usual way, but so when I say sum over heights, it means you sum over all the different configurations of heights that you're decided you're allowed to put on the lattice. The heights may be just some finite set of integers. And then the weights, instead of being just nearest neighbor, we're going to allow something slightly more general. If you have a face of the lattice, there's 4 of these heights around it, or 4 spins around it, and we're going to allow the interaction to depend on all 4 of them. So obviously nearest neighbor is a special case. So for Ising, we would just have interactions between 2 nearest neighbors, but I'm going to write it in a funny way, and for reasons that'll become obvious, I hope, why I wrote it this way. Instead of doing them on every site, I'm just going to omit half the sites. I draw the sites, but I don't put any spins on them. So A and B are just plus or minus 1. That's integer valued. And then these are the usual Ising Boltzmann weights. Okay? So hope that picture is okay. I'm just defining a lattice model the way many have done before me. But now I'm going to talk about lattice models where I can rewrite those heights, and that includes the Ising model that I just showed in terms of this fusion category stuff. Hubert mentioned this very explicitly yesterday and gave you an example of a lattice model that can be written in terms of the temporally Lieb algebra. There's lots of generalizations of this that people worked out, again, mostly in the 80s. But temporally Lieb goes back to the 70s. In fact, it was temporally Lieb who did the work that Jones rediscovered. People tried to rename the temporally Lieb algebra the temporally Lieb-Jones algebra, which actually probably would have been fair, but it didn't stick. Anyway, so again, that's the picture I just drew before. But the point is, now there's a lot of tensor network people here, so to try and relate this to something you all have seen before, instead, there's a completely equivalent way of writing this model in terms of a tensor network where it basically lives on the dual lattice. So I replace, these are just the usual matrices in the tensor network language, and then this would be called the physical spin. What it turns out is we can write our lattice model Boltzmann weights, such as a channel. I'll give you an example in a second, and then turn it into a tensor network. So this is not just analogous to a tensor network. It is identical. Mathematically, it's exactly what a tensor network person would write down once you write things in the correct way. And I hope at least that intuitively makes sense. And okay, so most definitely is not a generic lattice model I write down. However, it is an extremely interesting class of lattice models, including the Ising model, lots of others that you may have heard of. But one thing I want to emphasize, I think all rational CFTs, at least all that I know, have at least one such model, and typically more than one, but at least one model that you can write in this fashion. That's not a proof, and you could concoct some really complicated conformal field theories, and it would take me a long time to figure it out. But I would bet it's true, and even if it's not true, certainly almost any conformal field theory that anybody's ever studied, any rational conformal field theory, excuse me. So that rules out the stuff Hubert was talking about yesterday. All right, so let me give you one example of how this works. So in the tensor network language, what happens is, as I can say, I'm going to just write this as a two-state, what in the tensor network language would be the physical system, will be a two-state system with some weights that I'll draw this way. So just think of these as loops. So the dots are my original lattice where the heights live. And then in this tensor network, well, I have two choices. This is how you get a loop model. And I can weight the two ways loops can avoid each other at each of the vertices on this lattice by these two weights, WV. And then what turns out, so I haven't proven this, but this is what temporally Lieb buys you, and this is what lots of other ways of thinking about buys you. You can turn all these models for the minimal models of CFT can be turned into this model by some completely now standard manipulations. This is, let's say, what Temperley and Lieb did. Where it becomes a loop model where this number D is the number of loops, so depending on which minimal model you look at, determines the value of D and then these local weights. And just schematically, what always happens in these models, what you can turn these models into this partition function, you're summing over all configurations. They're loops in more complicated models. They're more complicated objects. One set of models has my favorite thing in the world. The chromatic polynomial is the topological weight. But anyway, you get this topological weight. So D to the number of loops is topological. It just depends on how many loops there are. And that doesn't depend on the paths of the loops. And then these local weights that just depend on whether they avoid. And the key thing that I'm asking you to trust me on is this huge class of models can all be written this way, but now we've got something topological out of it, and we can do our manipulations. And that's the point. So that's the rewriting. And anyway, so I think says what I just said. And so we can use these rules I told you about to manipulate the pictures. So that's one rule I told you about before. Here's another one I didn't write down before, which is if you have something coming in that's not the identity and then terminates on a loop, that's actually zero. It's a generic thing in any category. So this is the kind of thing that makes your life easier. You do these manipulations, and anytime you see that, the graph evaluates just to zero. And for us today, there's lots of things you can do with this, but for us today, it lets us topological defects. Okay, good. So that's the intro part. So everything I told you so far is pretty much ancient history. I don't think anything I said was not known in the 80s, and in fact, it would have been better known in the 80s because I think most people have forgotten it in the last 30 years. But anyway, so that's the setup. All right, good. So that's about half my talk. That's the setup. Now, the good part is we can just kind of reel off the results. Again, I'm not going to do the calculations, but hopefully I'll give you enough of the pictures so that you get the global picture. Okay, so a topological defect. We got our lattice model that's living on the square lattice, and say I want to make a defect that follows this path. Okay, well, anyway, so I just draw it there. Well, so the way I define the defect, so this slide is defining the defect. And so basically, you can think about it, you split open the lattice along the path. And then I insert these, well, quadrilaterals and trapezoids and these other shapes, but some kind of rhombus in between there. And then I assign a weight for the defect, which isn't necessarily the same. A priori, it's whatever you want it to be. I'll constrain it in a second. But you just wait, this is a defect, not yet a topological defect. This is a defect. In the tensor network picture, where it's the dual, you would have this line running through there, and then you would put a defect line, which I drew as green and squiggly. The green for there and there, not supposed to point out that inserting that defect would be like inserting the squiggly line there. Except the squiggly line's on the dual lattice, not on the original. Okay, so this is just a formula to say the words I said. So you sum over the partition function. Calligraphic Z within the presence of the defect is sum over all the configurations. Again, the product of the faces of the Boltzmann weights around each square, but then you get these Boltzmann weights along the defect. So this is the definition of a defect, not a topological defect. But now I want to make this a topological defect. So what a topological defect means is I can deform the path of the defect, so I can choose Boltzmann weights for that defect, the green things, the green funny-shaped things, so that the partition function doesn't depend on any local deformations. That's what I mean by a topological defect. And so you can see, well, what happens if I insert this here? Well, obviously I want to move that up to there and get the same answer. Well, this is the equation. And since in the partition function we're summing over all spins, we have to fix these around the edge for this to be true in general, but I can sum over that because that's internal. And so then this is the relation, and then there's another analogous one like that, and of course all the rotated versions of these relations. And you can easily see if you impose this and all its rotations, you'll get a topological defect. And this already shows you why the people who have studied this directly on the lattice have made real progress, but not much, because these are nasty and hard to try and solve by brute force. But the tensor category is going to let us do it. Now, again, for the tensor network people, in fact, this has been relabeled in that world. Frank Verstrada and company and his many members of his team written several papers on this, and they call it the pulling through condition because in the tensor network language it looks like that. I mean, these two are the same thing. Again, so this is not analogous. These are identical equations, just rewritten in a different language. Okay, so anyway, so that's what you're doing, and you're dragging the defect around, and the key thing is the partition function stays the same. Yeah. So the lattice models are not chiral. The algebra we're using would be that just of the chiral bit of the CFT. Yeah, no, it's right. So in a CFT there would be the left and the right algebra, which, well, typically not. Even most ones are isomorphic. We're just using one algebra and we're building lattice models. So a priori, in the Ising example, there is an Ising CFT and there is an Ising lattice model, and not surprisingly, the Ising lattice model turns into the Ising CFT, but that's not true in general. In other words, we use one of these categories to build a lattice model, and you'll get a CFT, but it's not necessarily the same category. The category in the CFT is not necessarily the same one. I'll make a comment there. Good. Any other questions? All right, so this is really the key slide of the thing. This is what we want to solve. And say you can do it by brute force. Again, people are smart and work hard and have gotten somewhere, but all that. Anyway, but the point is, let's give you a brute force example so people knew this. So for Ising, there's two kinds of defects. There's the spin flip defect, which just looks like this. So you have a spin A when you cross the defect. It has to be different. So plus has to be minus, minus has to be plus when you cross the defect. I remember in Ising we did this funny thing where we omitted half the degrees of freedom. This is why, the next one, there's a duality defect, what people call a duality defect. And so that one, again, there's some numbers here. It's a phase with a numerical factor. But the key thing is now notice we've shifted spin defect. You go on to the and we draw a big picture. That's too loud now. Draw a big picture. So the stars just label where the spins are, so we emit them on half the sites. But when you have a defect like this, you've shifted the spins to living on the other sublattice. And you find, well, if you choose this weight, and if the weights on the other side are the dual of the original one, then it satisfies these equations. So this is a duality defect. Now, some people have constructed these by hand before, but you'll see our picture even make things easier for Ising. Okay, so I told you all this stuff about categories and all that, but here's the so the point is we can now, for any lattice model that we build using the rules that I outlined, we can find a set of topological defects. We can find a defect for every single label in the category, or object in their language. There corresponds to a defect, so something solving those equations from there. So that's just, and you can prove in complete generality, that solves it. And one thing to emphasize again, you don't need to impose integrability. Now these models, these lattice models that can be written that way, are intimately related to lots of integrable models. But I'll give you an example at the end. Well, I'll make it clear. These are generically not integrable. But many interesting integrable models are special cases of such models, but generically they're not. But this works. This doesn't remotely use integrability. All you need is to write the model in this fashion. Granted, that's not generic. I emphasize that again. It's not generic, but lots of things are there. So this is the proof. That's the thing I showed there. You just manipulate these things around. The key thing, notice you have this thing here. The loop, the green loop wraps around there, and notice over there it's on this side, and you could do it the other way in there, and this is like the pulling through condition. So that's just schematically to get the idea of how that works. And it's any category. You can just prove it for all at once. It's useful to write things in operator language. Again, to use the current parlance, the transfer matrix is a matrix product operator. You just add, you divide you make a vector space or Hilbert space by, say, some row of spins, and in my world, this turns out to be typically the best way of doing it. And then the transfer matrix just adds these things on. So, and you can think of it a matrix when you pick a basis along this line here. What people in tensor network world would do, draw that thing. And the defect line then is just another MPO. You just add a string of those there. So this is for the defect line to create a horizontal defect line labeled by whatever field phi. So in Ising, if you wanted the duality defect, phi would be the sigma, and so forth. But then the key thing, what the defect commutation relations get you, is that this operator commutes with the transfer matrix. And so just draw pictures. It's no more work. Once you defined that, you just draw pictures. And what's remarkable now is these microscopic rules that we've used to define the model. So for example, the closed loop gets this weight d sub phi for a closed loop of type phi. Well, we can use these at the partition function. So in fact, it's easy to check that when you define these defects, if I nucleate a defect, the thing, all it does is multiply the partition function by this factor. But then we can deform the defect. And so we've made now a statement that the partition function in the presence of a topologically trivial defect is the same as that without the defect, but just multiplied by that number. Because all I do is create a defect that just multiplies by this sort of microscopic number. But then when I stretch out the defect, it gives me this thing. So this is a relation between two partition functions. So to give you an, give you an Ising example. Oh, sorry. Well, so if I did this for Ising, and that was so I drew the picture, so let me just say it here. So remember, Ising, the duality defect changes the couplings from dual to the original as you cross it. Well, what it's saying is this partition function, these two partition functions the same, and this is a duality defect, that's square root of 2. So it works. And we can now fuse these defects together, again, sort of a microscopic to macroscopic. And let's look at that one first. All right, so in Ising, in the Ising CFT, I wrote down that fusion rule a while. 2 sigmas give you 1 plus psi. And the same rule turns into the defect. So again, it's microscopic to macroscopic. Yeah, okay. Yeah, so I started about 5 after. Anyway, so again, so you fuse 2 defects together, and so what happens now is if I take 2 defects like that, well, I fuse them together and you get the identity defect, which is, well, if I have the pointer seems to be unhappy. But anyway, the identity defect and the spin flip defect. There's other ones too, just to show, even though my main example is Ising, you can do this for any of these models, and a famous one is the Fibonacci category. One thing to emphasize, for a given CFT, there's often multiple lattice models that give you the same CFT, and here, there. So this is one of them. And, well, anyway, or you can, multiple lattice models give you the same CFT, but you can go the other way around. The same category can give you different CFTs depending on what you take the couplings to be. And so in this case, you can get trichrotalysing over three-state pots, and then this thing exists as well. But here, one thing to emphasize, people often say duality is a symmetry, and it's easy to understand why, because in this couple slides back, remember I showed this operator, this duality defect operator commuted with the transfer matrix. That was the whole point of the defect commutation relations. So we typically call that a symmetry, but we typically don't call that a symmetry because it's not unitary. So usually in quantum mechanics when we do this, symmetries are unitary. And in fact, duality is not even invertible. It's easy to check. You do the duality defect 4 times, it's twice doing it twice, so that's not invertible. So it really isn't a symmetry. It's a duality, so don't call it a duality symmetry. The symmetry is not redundant. The symmetry is contradictory, so it's a duality. And again, physically, that's obvious because in the high temperature phase of the icing model, there's a unique ground state. In the low temperature, there's 2. They're not the same model. They're related, but they're not the same. And this defect shows how to relate them. All right, so let me go through very quickly now in my last 5 minutes some other applications. So we have this sort of generalized duality. We can do this for any model. So to go back to Ian's old results. So again, all I'm doing now is the same pictures I drew before. But I'm now going to label the boundary condition. So I drew this on the disk and label the boundary condition by some state B. And that's just, think of a vector space of all the spins or heights on the boundary. And I pick a configuration, and that's a boundary condition. Not necessarily conformal. But then what we can do is we can nucleate a defect. And I just told you all the defect does is multiply the partition function. So to get this equality of partition functions, emphasize this is not an equality of configurations, it's an equality of partition functions. You just divide by the quantum dimension. But then I can push, in the last one, I can push the defect all the way out to the edge. And then you can ask, well, how do I have a defect sitting right next to the edge. Well, the edge is just some vector in this space, whatever boundary condition I've chosen. Well, now the D I wrote down in the previous slide is just some operator, the D sub phi or D sub sigma. So all I have to do now is just absorb the defect in the edge, if you wish, by acting with this operator. So it sends this boundary condition to some other boundary condition. Just gluing it to the edge. And so what we've now related the partition functions of the two. And so in icing, for example, if you do the duality defect on up, you get the free boundary condition. And this is explicit. You just write it out. And using those defect weights I wrote down. If you start with free, this is why it's not in one of the many ways of seeing it's not invertible. If you act with free, you don't get fixed up again. You get fixed up plus fixed down. So we have this relation between partition functions, and what we've shown rigorously and exactly that these two partition functions on the lattice obey this relation, where we have the partition function with the original boundary condition and the partition function with the new boundary condition. And their partition functions are the same up to this operator. And so that's it for icing. It relates the thing and its dual. If you go to the critical point, this is exactly what Ian and Andreas called the ratio of G factors. So they associated this G factor, which is a subleading term in the free energy that depends on the boundary, and computing it outside of conformal field theory directly for specific boundary condition is quite difficult because there's all these non-universal things. But the ratio is universal because you divide out all the bulk stuff and you get this. But we just did this calculation exactly on the lattice. So it should match with the CFT. And, well, of course it does. Yeah. That's right. Yeah. We just proved it does. Yeah. Yeah, of course they do. Yeah, you do the calculation. They do. Well, I'm not saying it. We did the calculation. You have to change the couplings to the dual couplings. It's definitely true. It's definitely true.
It's maybe true provided the Boltzmann waves are given by
Yeah, of course. Well,
something that satisfies the factorization of the defect going through and all that.
yeah, but the Ising Boltzmann weights satisfy it. That's our entire point. Yes. Nothing to do with that. Yes, that was right. Yes. Again, you can do this for other models as well. Right, so I got about 2 minutes or something. Okay, so let me just flash some slides that show other things you can do with this. So you can make junctions of these defects. So even in Ising, as far as I know, this is new. Nobody ever. You can have defects join, and then there you can show that you can choose a Boltzmann weight for this sort of little triangle there, such that that's movable. Again, it's all topological, and the category gives you that. So then you can do, again, microscopic, macroscopic. You can do these F moves on the defects themselves, not just this microscopic stuff. And what this lets you do, for example, so I'm just going to flash the result. What this lets you do is compute, again, so this is an example of Bear. So this is what, spin structures, if you wish. And this is true off the critical point. You know this is true off the critical point. You wrote a paper on it. You showed this. So we can do this directly on the lattice. For generic theory, you can find these bases. You can do modular transformations, so you just draw a picture. So these are defects wrapping around with the vertices. That provides a basis for partition functions. You can do modular transformations. So the modular transformations just turn that picture. But again, I can manipulate that picture using these F moves I just showed you back into this canonical form, the Z ABC over there. And that's the answer. So again, it's totally generic, and all of them agree with that. And so that's I'll finish on, I'll show some transparencies, but the last thing I'll show you is, so that's a conformal partition function. And so we've conjectured that any time you have a lattice model that comes in, that in the continuum limit becomes a CFT, the category that describes the CFT is a bigger category. The lattice model category is a subcategory of this. So you can compute a diagram, and then by matching how the modular transformations work on the lattice between how they work in the continuum, we have conjecture for what how the lattice partition functions relate to the continuum ones. Right, so let me, so one other thing I'll just say it as I flash slides. You can compute dimensions of conformal operators by doing Dehn twists. That's right, to keep Hubert awake. I put this in, but I guess you're still awake. You can compute operators, and one of the things to show this, to emphasize, this is not integrable. There's integrable points in this phase diagram of some lattice model, but it makes a prediction that in any theory any conformal field theory you get out somewhere in this phase diagram, you're going to have some SU2 level K critical exponents. That's our lattice calculation. And sure enough, if you look at all the things Hubert and company identified, they always have some SU2 level K lurking. So those operators are there. So it's a huge constraint on any CFTs you might get out of your lattice model. Okay, there's some other applications too, but let me just flash. I'll flash some future possibilities, and sorry for running over.
Questions? I have one about the relationship to integrability. You said that it didn't depend on integrability, but some of the relations, like the pulling through relation, look very much like the Yang-Baxter equation, but maybe with slightly different indices. So is there an easy way to state, if it's not integral models, what is the class of models where there is this structure?
Yeah, so it's more like Brady. So with integral model, Yang-Baxter has a parameter in it, the spectral parameter of integrable models. And so that's that's a stronger constraint. So the way you Baxterize, one way of finding integrable models from these categories, you first write them like this thing, and then you work harder and find a solution to the Yang-Baxter thing with spectral parameter. That's what's called Baxterization. And so this is sort of not Baxterized. It doesn't matter what the coefficients of all these projectors are. At this stage, it still commutes. So that's why I say they're intimately related. So kind of for every model like this, you can, at least all the ones I know, there is an integrable model given by tuning the coefficients appropriate. In fact, typically there's more than one. But these are typically then special points like in that circle I flashed at the end. And yeah, so that's, so
is there something I could look for? Suppose I didn't maybe know exactly how to solve a model, but I could solve it on a computer or something.
Yeah.
With integrability, we know various things we look for to sort of tell if it's worth looking for a Yang-Baxter equation. So here, is there some simple...
Yeah, actually, you just put in a great plug for the talk I gave a week ago here. You weren't here, right? Yeah, so, yeah, so there's this way of looking for what I would call conserved currents. Some people call discrete homomorphicity. That's a simpler way. The typical way is just brute force. You just plug it into Yang-Baxter. But Yang-Baxter is so highly over-constrained that you can usually find... You can show it fails most of the time, and then occasionally it might work, and then you grunge it out. But yeah, there's this fancier way that yeah.
But if you didn't have integrability, you wouldn't have topological defects on the lattice, right? I mean,
Yeah. So it's sort of the fact. Well, I would say if you didn't have, I would say the more fundamental objects of these tensor networks are the more, and somehow, and integrable, or if you wish, which obviously are tangled up very much with quantum groups, so you can decide which one's the chicken and which one's the egg. But I would say the quantum group or the category or those are kind of this underlying structure, and integrable models are one of the consequences, and then this is another, obviously, tangled up deeply.
If I took a model that's not integrable, but based on some of these temporal algebras or something like a random Potts model in 2D, and asked you to build topological defects on the lattice, could you do that?
Yeah. As long as you took used the temporally Lieb generators to build them out. The point is the topological defect commutes with every temporally Lieb generator individually.
Fair enough. These defects, yes, okay. Okay.
Yeah. So yeah, I should have said it that way. So, right. So they commute with it individually, so you can stagger them or randomize, and it all still works. Yeah.
Yeah.
These are tensor network states on the lattice, but if you go to the continuum, you get the CFT. Do you have problems with long-range correlations?
Apparently not. I mean, the one thing that's not, I kept saying exact and rigorous, but the one thing that's not proved ever, except for the icing model, is that you can take this limit. And to me, that's a mystery. I mean, why? I mean, I say you write so. Oh, I guess one thing I should say. So the networks look non-local. So when I wrote it as this sort of d to the number of loops thing, that looks non-local, and then you might worry about long-range things. But the fact that to begin with, I had something that was local, and then, so in a way, it looks like I made the problem much harder by going from nice local icing nearest neighbor weights and writing in terms of these loops, which are non-local, and you have to worry about all this stuff. But what that buys you is then this. So if you didn't, So if you're looking at objects like what's the loop-loop correlator and the kind of stuff Zubair does, then they will be non-local. But as long as I'm only looking at local properties, it's okay. But yeah, that's not a proof, but that just always seems to be the way nature is.
All right, unless there are any urgent questions, let's thank Paul again.
Thanks.
Now we break for coffee.
Yeah, thank you. Yeah. That's right. So your question was exactly, so because